Welcome back to the series of lectures on high performance scientific computing. So, we have been looking at how to effectively program parallel machines, both shared memory machines and distributed memory machines. We have also in the last class looked at certain numerical techniques and algorithms which will help us to improve our parallel scalability and parallel efficiencies. It is always useful to program in the highest possible levels of abstraction to implement the scientific computing that is required. So, with an idea of this, it's better to use libraries which have been designed for very specific tasks of scientific computing rather than rewriting and reinventing the wheel by writing all the lower level codes that you need to do a certain simulation. The idea behind this is that if you use libraries or pre-written code, the chances of making errors are few. Plus, these libraries can be shared about easily, making things easier. Let us now discuss a few libraries which are very useful in the high performance computing spectrum. The first one that we will look at is specific to using CUDA devices, and this is called as a thrust parallel algorithm library. This is a specific set of libraries which have been written for CUDA devices which enable you to offload your compute into GPUs. So, what is Thrust? Thrust is a high level parallel algorithms library. It is an analog of the C++ standard template library which enables you to do a lot of functions very easily. It's essentially an abstraction layer which gives you good performance. And it also is extremely portable, which can take your code to different platforms. It's one of the most productive ways to program CUDA. Here is a simple code example of how Thrust is used. You basically have to include the Thrust header files so that the program knows or the compiler knows where to find the appropriate definitions. Then in the main problem, you can then invoke this by calling data types which are part of the Thrust library or which have been defined in the Thrust library. In this case, you can see there's a host vector which is a host vector of certain size. It also then generates random numbers from the start to the end of this host vector. Then there are function calls to transfer it to the device vector by simple assignment over here. For example, if I am just saying thrust vector device vector int dvec, it essentially allocates memory on the device for dvec and it takes a sizing from hvec. You're now assigning hvec. You're actually doing all the processes of allocating memory on the device and then transferring the device data from the host in one particular statement. And then you have other functions as well, like say explicitly sorting the data. Now you can call this thrust function sort to sort the device vector directly from the host without writing any particular code, and then you can do a copy back. So very basic algorithms have already been sort of implemented on the device for this Thrust library. So it's very easy to use. It comes standard with the CUDA toolkit. It's a header only library. It's also architecture agnostic. So it can be used over multiple architectures, and it is essentially you just have to compile the code and then run as long as the header definitions are correct. So it greatly increases the productivity. So you essentially have data containers such as the host vector and device vector. It allows you to do memory management like allocations and transfers. And then it also allows you to select certain algorithms which are already there. For example, the sorting algorithm that we did. So in the example of the code on the right side, you see in the first statement, we are allocating host vector with 2 elements. In the second statement, we are copying the host data to the device memory. In the third statements, we are writing device values from the host directly. Then we are doing the calculation on the from the data from the device. And then we are finally invoking certain algorithms on the device. And lastly, once it is done, we sort of release all the memory. So you have now taken several lines of code and sort of combined it with just a few calls. And that's how it increases the productivity. So Thrust gives us a large set of algorithms, almost approximately 75 functions within 125 variations in it. It gives us flexible user-defined types, user-defined operators as well. And you have a lot of algorithms which are already pre-coded for you. For example, reduce, which gives you a sum of a sequence. Find finds the first position of a value in a sequence. Mismatch, first position where the two sequences differ. You take an inner product. You can check whether two sequences are equal. You can find out the position of the smallest value using the min element algorithm. You can count the instances of a value using the count algorithm. You can check whether the sequence is sorted or not. And also, you can do a transformation of the sequence. Thrust interoperates with many different other libraries like OpenMP, Thread Builder Blocks, CUDA C, C++, cuBLAS, cuFFT, NPP, STL, CUDA Fortran, and the standard C++. So you can now use, as long as you're able to include Thrust headers, you're able to use Thrust library and its functions across all these particular modes. So if you have support for CUDA, Thread Builder Blocks, and OpenMP, all you need to just keep doing is recompiling with the appropriate flags. Essentially what you're saying is that, let's say that you had a hardware where you have NVIDIA GeForce GTX 580, you can then compile the code with the appropriate flag for it to run on the device NVIDIA GeForce GTX 580. Suppose you go onto a machine which does not have such a GPU but has a multi-core CPU like the Intel iCore i7. You can now recompile the code with the appropriate flag and then just rerun the code, and now the code will run only in the CPU mode. So you do not have to make any changes in the source code. By just recompiling the code, you can target it to different architectures. And this is really useful because every time we go to write a code, there are possibilities that you will introduce a bug or create a bug. And hence, here, once a code is verified, the same code will be able to run on multiple devices just based on the compiler flags. So what are the sort of the backend system options? The host systems that Thrust can use is C++, OpenMP, and TBB. The device systems that they can use is CUDA, OpenMP, and TBB again. You can use multiple backends within the same application. For example, if you're on a multi-core CPU with a GPU on it, you can now utilize the power of both in the same code. You can reduce, for example, the reduction operation can be done in parallel on the CPU, and the sort can be done in parallel on the GPU, depending on which task is suitable for what sort of hardware. You can call the appropriate functions for it to be done on the CPU or on the GPU. So typically, the potential workflow of trying to use something like Thrust is implement the application with Thrust. Then you profile the application, you identify bottlenecks, you then do the code modification to specialize the components as necessary with the optimized code, and then restart your process, reducing the bottleneck. And then you rerun the whole workflow again for it to get more improvements. There are several resources which are available on the given link, thrust.github.com, where you have documentation, examples, a mailing list where people can contribute, and there are regular webinars and publications. The next thing is we are looking at libraries for numerical linear algebra. Now, if you look at most computes, we reduce them into linear algebra problems, and we will now look at a few linear algebra libraries which give us quick access to functions for doing mathematical operations like BLAS, LAPACK, and ATLAS. So if you look at most scientific codes, the most amount of time that is being spent will be in numerical linear algebra, and also the most amount of memory usage will be in numerical linear algebra. This is essentially the construction of linear algebra systems, trying to do matrix-matrix products, matrix-vector products, doing operations such as factoring, forward and back substitution. This is where a code spends most of its time. So, whenever it is possible, we should rely on existing mature software libraries. The reason is pretty much simple of what I mentioned earlier, that every time you try to rewrite a code, it is inevitable that you will be introducing errors in it and bugs in it. So, once a code has been written, it is better, and tested obviously, it is better to reuse the same code as much as possible. Also, the idea of using these mature libraries is that then you can now focus on the higher level algorithm and not worry about the lower level code as much. Your code then will be more portable, less buggy, and will run faster and sometimes even much faster. So there is a repository of these codes in a website called www.netlib.org, which is maintained by the University of Tennessee and the Oak Ridge National Laboratory. Most of this code is in public domain, freely licensed, and most of it has an incredible legacy of still being written in Fortran 77, showing that these codes are nearly 4 decades old. That means they've gone through several sets of eyes which have looked for the code correctness, and you can be rest assured that the bugs that are there in this are absolutely minimal. One of these codes is BLAS, or Basic Linear Algebra Systems. It is written by the people who understood that the future benefits of standard kernel routines for linear algebra is very useful for programmers for code repeatability. And it is basically organized in 3 levels. The first levels, which was written in the decade of 1970s, looks at order n operations, which look at operations like addition of vectors, scaling of vectors, dot products, norms, and so on and so forth. The second level routine, which work on order n square, was written in the mid 80s. They look at matrix vector operations, matrix vector products, triangular matrix vector solves, rank 1 and symmetric rank 2 updates. The third level routines were written in the late 80s, looked at n-cube operations, which are matrix-matrix operations, matrix-matrix products, triangular matrix solves, and low rank updates. So, if you look at the BLAS operations, the level 1 operations such as addition and scaling do operations like alpha into x plus y. They look at dot products and norms, like multiplying the transpose of x with y, taking the second norm of x, taking the first norm of x. Level 2 operations look at matrix vector products, right, like alpha ax, where capital A over here is a matrix and y is a vector, or alpha A transpose x plus beta y. So these are matrix vector products. We also look at rank updates, rank 1 updates, rank 2 updates. Anything that is denoted in capital letters is typically a matrix. Anything that is denoted in small letters is a vector, and anything that is denoted in Greek alphabets like alpha and beta are constants. So it does rank 1 updates, rank 2 updates, triangular solves. And in the level 3 operations, you have matrix products, right, like alpha AB plus beta C, rank K updates like alpha A transpose plus beta C, rank 2K updates like alpha A transpose B plus alpha B transpose A plus beta C, and triangular solves. Now let us look at what is the naming convention of these BLAS routines. So BLAS routines have a Fortran inspired naming convention. They typically have a prefix, a data type, and an operation. The data types that it can work with are single precision real, double precision real, single precision complex numbers, and double precision complex numbers. Each of this is denoted by the alphabets S, D, C, and Z respectively. And then you have the different operations. For example, you have the AXP operation, AXPY operation, which essentially will create a vector for alpha into x plus y. Similarly, you have a dot operation, which creates a dot product between two vectors, which is the inner dot product. You have the norm operation, which takes the norm of a vector. So it could be the second norm in this case. And it could also take a sum, which is the first norm of the case. For example, the cblast d dot function essentially is doing double precision real calculations and is giving you the dot product of the two vectors. In level 2 and level 3, the naming convention goes as the prefix, data type, the structure, and the operation. Now, if you define the matrix structure, it tends to make the calculations more convenient and more computationally effective. For example, the matrix structure could be TR, triangular, TP, packed triangular, TB, banded triangular, SY, symmetric, SP, packed symmetric, SB, banded symmetric, HY, Hermitian, HP, packed Hermitian, HN, banded Hermitian, GE is a general, and GB is banded general. The operations could be MV, like matrix vector multiply, which does alpha AX plus beta Y. It does operations like SV, R, R2, which are basically rank 1, rank 2 updates. Matrix multiplies like alpha AB plus beta C, and rank 2k updates. So essentially, if you have a function which is cblast DTRMV, it will say it's a double precision real triangular matrix vector product. cblast DSYR2k is double precision real symmetric rank 2k update. So this is the sort of naming convention these functions use, and then you'll have to provide the appropriate arguments for each of these operations. When you're trying to use BLAS efficiently, it is always better to choose a higher level BLAS routine over multiple calls to a lower level BLAS routine. For example, if you want to do an operation on matrix A, which is denoted over here, where A belongs to a matrix of real numbers, which is m cross n, the vector xi is of real numbers of length m, yi is set of real numbers of length n. You have two choices. I can take k-separate calls to the level 2 routine cblast dger, which will do this mathematical operation over here, or a single call to the level 3 routine cblast dgemm, which will give me the operation like this. The level 3 choice will always perform better because it has been customly written to do these kind of operations, whereas when you break it down, it will have to do several data accesses to do the level 2, the multiple level 2 operations, and the calling overhead will start dominating and will not be as efficient as a single level 3 call. So the question is, why should I bother using BLAS when writing our own routines are easy, right? I can do, let's say that I have to do an operation where I have to take the matrix A and add x multiplied by y transpose, where x is in the set of real numbers and is m cross n, x is m cross p, again in real numbers, and y is n cross p, again in real numbers. Now I can go and write an explicit code like this for mat multiplication and addition, and which could give me the same solution. But this is not efficient. Similarly, you can look at Gauss elimination, which is Ax is equal to b. So when we try to solve Ax is equal to b using Gauss elimination, we know that we have learned in high school that how to go about solving it. The first is we have to make A an upper triangular matrix. Then we have to solve the resulting system using back substitution. So typically this is what the operations look like. You first tend to zero out the first column through row matrix manipulations. You tend to make it into an upper triangular matrix. You go through it with column by column and after each iterations. And once that is done, then you go ahead and do a back substitution. Now we are trying to refine the Gauss elimination algorithm. So in this, for each column I, we can zero it out below the diagonal by adding multiple rows of I to later rows. Then for each, we can go ahead and do the loop for each row j below row I, and then add a multiple of row I to row j according to the math shown over here. I can now remove the computation of the constant temp by ai, I from the inner loop by introducing this temporary variable m, and that will now increase my efficiency. Then, so the last version then transforms into this sort of an operations, and then we don't need to compute zeros below the diagonal column because I already know that below the diagonal column everything is a zero, and I can just go and put it up over there. So now I have made these things more efficient. I can now store multipliers m below the diagonal in the zeroed entries for later use. So I can start putting it in this a, j, comma I, and I then reuse it over here after I compute m. So that means I have taken away the usage of m, variable m. So this is now how the last version looks like. I can make it further efficient by splitting the loop for j from I plus 1 to n and for j I plus 1 to n again. So for each of this, I can go ahead and do this. Then finally, if I look at the last matrix operation, this will come out to this. So this involves a lot of steps. But now I can express this matrix using a matrix plus operation. So I have now reduced my problem to this statement which is shown in red. And I can now do this with a BLAS1 scale vector, this is essentially scaling a vector. This statement is essentially scaling a vector. And this is a BLAS2 rank 1 update operation. So I can now increase the speed by just using this BLAS1 and BLAS2 operations. I can now improve performance through blocking. Blocking is used to improve performance of matrix vector and matrix multiplications, Cholesky factorization, so on and so forth. Let us say that I have an operation like A plus X Y transpose. So I have two matrices, rather three matrices A, X and Y. I can sort of put them in some blocks where I take A and put it into four sub-blocks, A11, A12, A21 and A22. I take the vector X, or rather the matrix X, and make it into two sub-blocks, X11 and X21. Similarly, I do it with Y11 transpose and Y21 transpose. So now the operation AXYT has now been transformed into these sort of optimal block sizes. So we need to figure out what the optimal block size and the order of computations are, and this depends on the details of the processor architecture, what is the cache of the processor, and how much memory the processor has. All these factors will determine how fast this is going to go. Then we look at LAPACK computational routines. LAPACK computational routines allow us to do factorizations for LU, LLT, LLH, LDLT, LDLH, QR factorization, LQ factorization, and so on and so forth. They also provide us ability to do symmetric, Hermitian, and non-symmetric eigenvalue decompositions. It allows us to do singular value decomposition and generalized eigenvalue and singular SVDs. So LAPACK essentially contains subroutines for solving linear systems and performing common matrix decompositions and factorization. It was first released in 1992 and supersedes its predecessors such as IcePack and LinPack. It is built on top of BLAS, so it supports the same data types, single, double precision, real and complex, and matrix structure types, same as BLAS. It essentially uses BLAS for internal computations. And the routines are divided into three categories: auxiliary routines, computational routines, and driver routines. So the driver routines then call a sequence of computational routines to solve standard linear algebra problems, such as Ax is equal to b, or the least squares where we need to minimize b minus ax2. It also solves problems like the least norm, linear least norm, where you need to minimize the norm of y, subject to a certain constraint. So it looks at generalized linear least squares problems where you need to minimize the second norm of c minus ax. We need to minimize the norm of y, subject to certain constraints like bx is equal to d, and subject to another constraint d is equal to ax plus by. We also have the Intel Math Kernel Library. The Intel Math Kernel Library is optimized for Intel chips, which is basically the Pentium, Core, Xeon, and Itanium CPUs. So typically we use benchmarks for high performance computing on the Intel architecture. It comes with the Intel compiler suite, and it's pretty much free on the Linux platform, though it's paid on other operating systems. It has basically developed extremely efficient versions of BLAS, Spare BLAS, LAPACK, ScalaPack, VML, VSL, FFT, PDE, and other nonlinear optimization on Intel hardware. So BLAS and LAPACK is also available on GPUs. So NVIDIA CUDA math libraries, which are optimized for NVIDIA GPUs, like cuBLAS, cuSparse, cuRAND, and cuFFT, the CUDA math library, and then we have already seen what Thrust is. Supposingly that you have another accelerator apart from NVIDIA CUDA, you also have the AMD APP ML, the Accelerated Parallel Processing Math Library. This is for AMD GPUs. This is also based on BLAS and FFT, and it is offered on Linux platforms and Windows platforms for free. Then you have third-party libraries like CULA, which is paid, which is CUDA LAPACK, Magma, which is free, which is based on OpenCL and uses LAPACK. Finally, we also see the PETSI, or the Portable Extendable Toolkit for Scientific Computations. Scientific computations, parallel linear algebra in particular, linear and nonlinear solvers. So this toolkit contains high-level solvers, but also low-level tools to make your own scientific code. You can take this PETSI as sort of a Lego block, where you can take bits and pieces of it and build your own application around it. It has inherently much support for parallel computing underneath, including MPI. The main reason to use it is that it is very powerful, well supported, and the fact that you can program at a much higher level and not bother with the details of parallelization. So PETSI targets not only parallel programs, but it also targets serial programs. It looks at linear and nonlinear problems. It can use finite difference and finite element methods, and looks at both structured and unstructured problems. So what is there in PETSI? It essentially has a bunch of linear system solvers, both for sparse and dense matrix. It also has techniques, both iterative and direct. So it has support for nonlinear system solvers. It has tools for distributed matrices, and it supports profiling, debugging, and a graphical output. A lot of the PETSI documentation is available on the web page, and you can also get the PDF manual over here. So this is how the level of abstraction looks like. Right on top, you have the application codes, which is doing the science that you are interested in. Those interface directly with the nonlinear equation solvers, which are looks like SNES. Also, the time integration algorithms, or the time stepping algorithms, TS. All of this is based on certain numerical algebra, so you need the Krylov subspace methods, which solve the bulk of the iterative numerical linear algebra. And to improve the condition number of these matrices, you have preconditioners, which allow you to work with it. Underneath this are the most important data sets, which are matrices, vectors, and the index sets. They in turn call the internal libraries of BLAS and MPI, which allow you to do numerical algebra at a higher level, and MPI enables you to distribute the problem onto many nodes and solve this problem in a parallel manner. So what are the kind of numerical nonlinear solvers do you have? You have Newton-based methods, line search, trust regions. You have different time steppers like Euler, backward Euler, pseudo time stepping. The Krylov subspace methods is also very large. You have GMRES, conjugate gradient, CGS, BiCG-STAB, Richardson, Chebyshev, and others. The preconditioners that are there in PETSI are additive Schwartz, block Jacobi, ILU, ICC, LU, and others. And the kind of matrices that PETSI can work with are compressed sparse row, block compressed sparse row, block diagonal, dense, and other methods. It also works with a variety of index sets. But PETSI does not do everything. It needs to interface with other software. For example, if it needs to do dense linear algebra, it interfaces with ScalaPack and PLAPACK. If it needs to do grid partitioning, division of the problem, it integrates with Parametis, Jostle, or Chaco. If it needs to call an ODE solver, it calls PVODE. Eigensolvers, including SVD, it calls things like SLEPC, and optimization is done by tau. PETSI is already layered on top of MPI and has basic tools. It has elementary data types between processors. Intermediate PETSI, where you can insert matrix element at an arbitrary location, do parallel matrix vector product. You do not need to know much of the lower level MPI when you use PETSI. All of it is sort of hidden from the user, and you do not need to write explicit codes like MPI calls and MPI sends, write implicit synchronization statements like MPI barrier, so on and so forth. So all PETSI objects are defined on the same communicator and can interact only if they are on the same communicator. Remember, when we initialize the MPI program, we define a single communicator. All the parallelism is through MPI. There is no OpenMP that is there, but you can still use shared memory programming in the distributed mode by running all the MPI processes on the same code. The same code works because you're writing at a much higher abstraction level, the same code works in sequential and in parallel modes. So it's an object-oriented design. PETSC uses objects, vector, matrix linear solver, nonlinear solver. And you can go ahead overloading this operators. So if I say mat multiplication of ax, y, where y is the output of ax, it will be the same. The line of code in the top level code will be the same for the sequential code, for the parallel code, for the dense matrix, for the sparse matrix, so on and so forth. PETSC will underneath call the appropriate function. Thank you.